Next up, Chapter 5, which is all about clouds and stability. This chapter is also divided into two PowerPoints. This is 5A. After this will be 5B. This chapter is going to be dealing with the concept of atmospheric stability or instability, the types of atmospheric stability or instability, and cloud development. So whenever you see a cloud form in the sky in front of you, or clouds are moved overhead from some other location, there's some sort of a lifting mechanism going on that causes air parcels to rise off the surface of the ground, expand, and cool, and for clouds to form. And this is really a function of whether the air is stable or unstable. So we will explore these concepts in depth in this chapter. So this is Chapter 4A, PowerPoint. Talking specifically about the concept of atmospheric stability. It's basically like this. Stability is the state of equilibrium in terms of atmospheric movement. If the air is stable, then no vertical movement, upward movement occurs, meaning that a blob of air, a parcel of air, starts rising from the surface and maybe only gets up so high above the surface, and then it's forced to sink right back down. If the air condition is one of stability, then that means there is no vertical movement. Stable air resists upward or vertical movement of air. If we're talking about the Earth's atmosphere, of course, how clouds form in the first place is that a rising parcel of air expands and cools, and then, of course, if it rises high enough and cools even more, then it reaches the dew point and condensation occurs and a cloud forms. So a rising parcel of air expands and cools, while a sinking parcel of air, meaning a blob of air above your head that's forced to come down to the surface, is compressed and it warms. Obviously, since the weather around here, the Central Valley, is warm a great deal of the year, and we don't have a lot of clouds unless we finally get a storm that moves in, we often have mostly sinking air as opposed to rising air. So let's back up one step. What in the world is a parcel of air? Way back in the 90s when I did television weather here in Fresno, I used to go to grade schools because the teachers would invite me to talk about the weather to grade school kids, especially, say, 4th grade on up. And I used to call parcels of air blobs of air, and the kids used to think that was very funny. But, you know, in reality, that's actually the case. A parcel of air is a small theoretical blob or volume of air that can expand and contract freely as it rises or sinks. So a rising blob of air is going to expand and cool, and a sinking blob of air is going to compress and warm because you're forcing the air molecules into a smaller space. Clouds form as air rises, cools, and condenses, as has been mentioned before. If a parcel of air expands and cools, or compresses and warms, and that parcel of air doesn't have any kind of an interchange of heat energy with its surroundings. In other words, you haven't turned on your weather smurfing machine and inserted heat into the blob of air or taken heat out of the blob of air. If that blob of air expands and cools or compresses and warms with no interchange of heat within its surroundings, this is called an adiabatic process. We have a fancy college name for that, an adiabatic process. As long as the air in question, the parcel of air in question, is unsaturated, meaning the relative humidity is less than 100%, the rate of temperature change, the rate of adiabatic cooling or warming remains constant. Science has found this to be 10 degrees Celsius per 1,000 meters, or 10 degrees Celsius per kilometer. This is what we call the dry adiabatic lapse rate. This is how temperature changes for air parcels that are unsaturated, or dry as it's called, meaning the relative humidity is less than 100%. A parcel that has a relative humidity of less than 100% will always have a temperature change of 10 degrees Celsius per kilometer, decreasing as it goes up, or the temperature will increase by 10 degrees Celsius as it sinks or goes down. Dry adiabatic lapse rate. If the rising air cools to the dew point, now the air has become saturated. The relative humidity is 100%. Condensation occurs and a cloud forms, and latent heat is released in that process. That rising parcel of air in which a cloud has formed can no longer cool at the dry adiabatic rate because now the air is saturated. If it continues to rise, the cooling will be at what's called the moist adiabatic rate. The moist adiabatic rate is not constant. It varies greatly depending on the temperature of the blob of air you're talking about. The warmer the air is, the lower the moist adiabatic rate is. And as you can imagine, the amount of moisture in the air varies from place to place and from time to time around the world. So that's why the moist adiabatic rate is not constant, like the dry adiabatic rate is at 10 degrees Celsius per kilometer. Table 5.1 in your book shows the variability of the moist adiabatic lapse rate and how it's so dependent on the air temperature and the pressure of the air. Now, down near the surface, the pressure is close to 1,000 millibars. So let's just use that for example. And so, for instance, if the temperature on the surface is 20 degrees Celsius at 1,000 millibars, which is about 68 degrees Fahrenheit, the moist adiabatic lapse rate, or sometimes called the wet adiabatic lapse rate, is 4.3 degrees Celsius per kilometer, which you can compare to the dry rate, which is 10 degrees Celsius per kilometer. So you can see how that varies. The moist adiabatic lapse rate varies depending on the pressure of the air and the temperature of the air. So now let's talk about different conditions of stability. This is a situation which is called absolutely stable air, or absolute stability. We have a graphic here that shows absolute stability in dry air and also for moist air. We have an imaginary helicopter that's taking your imaginary parcel of air and lifting it up in 1,000 meter increments to make it nice and clean and understandable. All right. So if we assume that the air is dry, as in the left-hand graphic, and we start with an initial temperature on the surface of 30 Celsius, then we go up 1,000 meters, 30 will become 20, and 20 will become 10 at another 1,000 meters up, and 10 becomes 0. So you can see that the temperature of the parcel is decreasing at the dry adiabatic lapse rate. Now you see that other line there, that solid gray line. That's called the temperature in the environment, the environmental lapse rate. That's actually data that's derived from launching that balloon with the instrument package we discussed earlier called the radiosonde. So you can see the temperature of the environment, and the gray line called the environmental lapse rate is drawn to represent that, with a 4 degrees Celsius per 4 degrees Celsius decrease in temperature as you go up for every 1,000 meters. As long as the environmental lapse rate line is to the right of the dry adiabatic lapse rate, in this case, then you have absolutely stable air. The air will rise, but it'll want to come right back down from where it started. Now, the graphic on the right is an example of absolutely stable conditions for moist air. Same deal. We are given for this problem a moist adiabatic lapse rate of 6 degrees Celsius per 1,000 meters. So it's not 10, but it's 6 now because the air is now saturated. So that means the temperature decreases 6 degrees for every 1,000 meters you go up. 30 becomes 24, 24 becomes 18, 18 becomes 12, and so on. But in each case, when you plot that against the environmental lapse rate, the environmental lapse rate is still to the right of the moist adiabatic lapse rate, which means the air will want to sink right back down where it came from, which is absolutely stable air. How does the air stabilize? Well, the air becomes stable as the air aloft warms or the surface air cools, or a combination of both. How can the surface air cool? Well, the sun goes down. You get nighttime radiational cooling of the surface. Or if you get air on the surface that's colder, that's transported in from somewhere else, like a cold front coming in. Or the air is cooled as it moves over a cold surface. So these are ways that stability is actually enhanced. Now, this is a very important concept. It's called the subsidence inversion. And what this means is basically if you take a layer of air that's above your head, several thousand meters up, and you make it sink down to the surface, it'll tend to warm up as it sinks. When an entire layer of air over 1,000 meters thick, as in the line XY in the graphic there on the right, and it covers a large area, it's forced to sink or subside, the entire layer is going to warm by adiabatic compression at the rate of 10 degrees Celsius per kilometer. You're assuming this air is dry. The air becomes compressed by the weight of the atmosphere, and it shrinks vertically. So the upper part of the layer sinks farther, and it warms more than the bottom part. After sinking or subsiding, the top of the layer ends up actually being warmer than the bottom part. These subsidence inversions essentially is what will cause a heat wave in the southwestern United States in the summertime. Those days when we get like 110, 112 degrees, that's because of a subsidence inversion. So the layer XY above your head is initially 1,400 meters thick, but when you sink it down to the surface, X prime Y prime then becomes 1,000 meters thick, and then the upper layer of that upper part of that layer is now actually warmer than the lower part of that layer. Subsidence inversions are especially important in air pollution meteorology, and we think of course, the LA Basin as being a very polluted place. The San Joaquin Valley has rough air pollution issues as well. There is no question about that. But in the LA Basin, it's especially aggravated because you've got millions and millions of people down there. In the summertime, you have cool ocean breezes coming in right near the surface. That's the marine layer. And then you have these subsidence inversions with warm, dry, sinking air with warm, high pressure over the top of our head in summer. The sinking air tends to limit the volume of air in which pollutants on the surface can disperse. We call that the mixing layer. When you have a shallow mixing layer, you have a very high concentration of air pollutants near the surface. On the California coast, in Southern California specifically, this situation is enhanced by this cool marine layer near the surface. And then, of course, you've got the sinking warm, dry air aloft. That's high pressure aloft. Here in the California interior, it's enhanced by topography. Here in the San Joaquin Valley, we're surrounded by mountains on three sides. The Coast Ranges to the west, the Sierra Nevada to the east, and the Tehachapi Mountains to the south. So basically, if we have warm, dry, sinking air over the top of our heads, you get warmer air aloft, trapping cooler air below, and that tends to trap the air pollution right down here on the valley floor, where, unfortunately, we have to breathe it. Now let's move to absolutely unstable air, absolute instability. Basically what that means is this, and this works for both dry air and saturated air, or wet air, if you will, moist air. So if we're given the dry adiabatic lapse rate of 10 degrees Celsius per kilometer, which we were given earlier, we start with an initial temperature of 30 degrees Celsius, and the air is dry, so the temperature is going to decrease at the dry rate. All right, 30 becomes 20, becomes 10, becomes 0, just like before. But our environmental lapse rate is not 4 degrees Celsius per kilometer like it was in the stable example. It is now 11 degrees Celsius per kilometer. All right, so what happens is that the dry adiabatic lapse rate is less than the environment, therefore the air will continue to rise, and it's considered to be absolutely unstable. The graph on the left indicates how this works for dry air, but it also works for moist air. This is especially important because when you have absolutely unstable atmospheric conditions and you have moist air, there's a high probability you're going to get rain or even thunderstorms. So we're given the moist adiabatic rate for the right-hand problem, 6 degrees Celsius per thousand. So our surface temperature of 30 then becomes 24, becomes 18, becomes 12. All right. The environmental lapse rate still remains at 11. We haven't changed that from the left-hand graphic to the right-hand graphic. So obviously the environmental lapse rate is a much steeper lapse rate than the moist rate. So again, the air will continue to rise based on its own buoyancy, and this is considered absolutely unstable air, which may very well produce thunderstorms in the moist air. On the dry air side, it's just going to be a windy day. Then we have what happens most of the time in the atmosphere, which is called conditional instability. In a conditionally unstable atmosphere, the air is stable with respect to dry air near the surface, but unstable with respect to wet air aloft. For example, on the left-hand graphic, with the environmental lapse rate of 7 degrees Celsius per kilometer, that graph is to the right of the dry adiabatic lapse rate, which indicates that the air is stable with respect to dry air. But now, if we make the air moist, as in the right-hand graphic, now the environmental lapse rate plot is to the left of our adiabat, which indicates that the air is unstable. So conditional instability means that the air is stable with respect to dry air, but unstable with respect to wet air. So if the environmental lapse rate is between the moist adiabatic lapse rate and the dry adiabatic lapse rate, then that is conditional instability, which actually is the condition in the atmosphere most of the time. This is an example of how conditional instability can work with respect to dry air near the surface, but moist air aloft. After the cloud forms and the parcel continues to rise, you can see that inside the cloud, the temperature of the parcel is actually warmer than the outside environment. So that's why conditional instability means that the air is stable near the surface with respect to dry air, but unstable aloft after the cloud forms with respect to saturated air. This ends PowerPoint 5A.